on YouTube in 40 seconds, more or less. But you can continue the talk, no problem.
Okay, no, now I'm just curious I'm doing one thing. I'm going to connect on YouTube on the other laptop.
Okay, that's good.
No, that's just good. See what I will mute because so I'm just curious about what is going on.
You only need to turn off the sound.
Yeah, I did it. I see it works because it's not working my internet, but okay. Oh no, die.
How things work there, Raffaele?
What do you mean?
The semester
okay, we start we are teaching in a blended way. So we both are online and also live. So some students come to the classes, some students are online. But to be honest, it's not working very well. And the situation now is becoming very, very, very bad. So my impression is that we will be locked soon. And we will go online soon, just online.
Yeah, I saw the situation in Spain and the United Kingdom.
But in Italy it's becoming the same. Soon it will be the same.
Yeah.
Okay, no, what a pity that in my laptop internet is not working. No, it's working. Okay, just have to look at the link that you sent me yesterday. So let's see if I find it. Otherwise, okay.
Yes.
You tell me when I have to start.
I will introduce you in just now.
Okay.
I will introduce you in Portuguese as you understand everything, do you know?
Okay, yeah, please.
Ok. Thank you so much. Bom, boa tarde para todo mundo. É um grande prazer receber o Raffaele Argiento aqui no nosso seminário dessa semana. O Raffaele já esteve, felizmente, visitando o nosso departamento há algum tempo atrás, nos deu um curso de Estatística Bayesiana na Paramétrica, que foi bastante legal. O Raffaele é um jovem pesquisador bastante ativo. Ele fez a graduação dele na Universidade de Nápoles, se formou em matemática, depois ele obteve o grau de doutor em estatística pela Universidade de Bocconi. E aí ele trabalhou em vários lugares, que esteve como professor visitante em vários lugares também, mas ele ficou por muito tempo como pesquisador no Seminário. Depois ele ficou um tempo também como professor na Universidade de Turino, né? E agora ele decidiu voltar para Milão novamente, né? E ele está lá na Universidade Cattolica. Qual é a pronúncia correta del Sacro Cuore?
Cuore.
Sacro
Cuore.
Ok.
Coração.
I know. Mas, além de trabalhar e ser um professor que gosta de ensinar, pelo que eu já pude perceber da vida dele aí, ele também está se envolvendo com a parte de organizações de encontros, né? E ele agora é membro da organização do Bayesian Young Statistician Meeting, que deveria ter ocorrido esse ano, lá em Cunningham, na China, e ele foi postergado em função da pandemia. E ele já há algum tempo, ele é diretor executivo do que é o ABS, que é o Applied Bayesian Summer School, na Itália, que, em geral, tem uma programação fantástica, são minicursos que são oferecidos regularmente, eu já tive até a oportunidade de participar de um deles, foi realmente muito legal. Então, isso está sempre sob a organização do Raffaele. E Raffaele é um cara extremamente ativo, ele é um dançarino de mão cheia, para quem não quer saber o lado B do lado de Raffaele, né? E na parte de pesquisa, ele se dedica muito à parte de desenvolver métodos e modelos na parte de estatística bayesiana não paramétrica, não só nisso, né? Mas é uma das áreas que ele se dedica com com mais intensidade, e também na parte computacional, não só na teoria. E ele recentemente teve um artigo aceito no JASA, né? E eu fiquei muito feliz em ver isso. E o Raffaele, e antes que eu me esqueça, eu devo agradecer demais ao Raffaele, porque eu o convidei para dar esse seminário há uma semana atrás, e ele, numa sexta-feira à noite, ele está no departamento dele, lá em Milão, e dando seminário para a gente. Então, eu não tenho como lhe pagar esse favor, né, que você me fez. Muitíssimo obrigada por aceitar, Raffaele. Eu vou passar a palavra para você, e aí eu vou me deixar totalmente muda aqui. Se você precisar de qualquer coisa, é só falar que eu volto, tá certo?
Ok. Obrigado pela apresentação. I don't know. Gostaria de falar português, mas como sabe, não falo. Then I have to speak English. So really, thank you for this wonderful introduction. Thank you, everyone, to be connected. And I'm happy to give this webinar. This is my first webinar. I'm getting used to teaching online, but now I'm going also to make this experience of giving a talk online. So I think that you will see better if this is the better way that I can project my slides. So as you can see from the title, in this talk, I'm going to discuss a quite a standard model in statistics. Actually, I'm going to deal with finite mixture model. But I'm going to look at this model from a new perspective. I'm going to look at the finite mixture model from a Bayesian non-parametric point of view. And I will be more clear what I mean by looking at a finite mixture model from a Bayesian non-parametric perspective. Let me mention that this is a joint work with Maria De Iorio, that is currently in Singapore at the Yale NUS University. So I hope that everyone, all the people that are connected, are familiar with mixture model. Here I have an introduction in these slides. Mixture models are a very powerful and statistical tool when dealing with data that came from heterogeneous population. What I mean from heterogeneous population? I mean that I assume that data have arisen from M groups, each group being modeled by a parametric density that I will denote by F. Or let me be even more clear. This is an example, this is a textbook example, where on the x-axis I have the time of eruptions of the old Faithful Geyser in the Yellowstone Park. While on the y-axis I have the length of this eruption, the waiting time. Sorry, on the x-axis, the length of the eruptions, on the y-axis, the intertime, okay, the waiting time between one eruption and the other. And by visual inspection, we can see that here the population is heterogeneous because we can recognize at least two subpopulations. One with eruptions that are short in time but quite frequent, and another one of eruptions that are longer in time but less frequent. So we want to, in this framework, the goal is from one side to reconstruct the multimodal density that generated the data. And we will call this task density estimation. On the other side, we would like to perform model-based cluster analysis. What that means, we want to recognize from which population each data has been generated. For instance, you can see in this plot that I clustered the data in 4 subpopulations. The red and the C and 1 are the two that I recognize by visual inspection, and I have also other two small subpopulation, the green and the blue. The green and the blue. Now, let me just mention that I will refer to the density that represent the distribution of the data in each group as component of the mixture, while the relative frequency of each component will be denoted by W and will be called weight of the component. Okay, so here a little bit of notation. Usually, this is the standard finite mixture model in Bayesian framework. On the first line, I have the sampling model where the data conditional to two vector of parameters W and tau are IID from this weighted sum of kernel, that is from the mixture model with components F, tau H, and weights W. Since I'm Bayesian, I have to assume prior on my parameter. In particular, I can assume a prior on the number of components that I will call Qm, and conditional to the number of components, W usually are assumed to be Dirichlet distribution. And this is quite a standard choice because we know that the Dirichlet distribution has support on the simplex, so that W will sum up to 1, while the parameter tau H that identify the density within each component usually are considered IID from a prior that I will denote by P knots, and I will call centering measure, and this notation will be much clearer in 2 slides. Now, if this is the standard hierarchical representation of a mixture model, let me mention that this representation is not useful from a computational point of view. Why is not useful? Because of this sum in the sampling model. Okay, also from the maximum likelihood point of view, the fact that in the sampling model we have this sum is a little bit add some difficulties to the computation. So what usually statisticians do, we introduce some latent variable that here are denoted by J1, Jn. What are these latent variables? They are just component indicator. J1 just tell me from which component X1 has been generated. For instance, component of 2. J2 will tell me from which component X2 has been generated. For instance, component 3, and so on. Now, given the component allocator, the data are independent each from its kernel density. And these component allocators usually are integer between 1 and n that conditionally to W are IID from a multinomial density. So the sampling model this time is written on 2 lines, while the usual prior is still the same that before. This is still the same model. I'm just wrote it in a different way that is much convenient from a computational point of view. But now there is a crucial observation from my talk. These latent variable J1, Jn are important just because they identify from which component data has been generated. Their value is not important. So the fact that J1 is 1 or 10, or maybe J1 can be a color, can be red, as in my previous slide. So the value of J1 is not important. The important is the fact that J1 identifies in a unique way the component of data X1. So I can introduce a new parameterization where the cluster allocator are θ1, are θn, or exactly the parameters that identify the kernel within each mixture. So this will be parameters that you, in a unique way, will identify the component of each data. So they are still a latent cluster allocator. Their value will be not an integer, but they will correspond with the parameter of my mixture. But this time, these latent variables are not multinomial, but I can write that they are conditional to P IID from P, where P is this discrete random measure with support the point tau that are the point that are the parameter of my mixture, and with weight W, the weight of my mixture. So you see, I'm writing the sampling model in a different way by using a new parameter, this parameter P, that is a random measure. Now observe that this random measure is just a function, is a unique function, is completely determined when I have the parameter W, tau and M. So instead of writing the prior using this two line, I can say that my parameter P is distributed according to the finite Dirichlet process. So I have a new representation of my mixture model that is a typical representation of a mixture model in a Bayesian non-parametric framework, where the mixture is represented through these three lines, where P is a parameter that is a random process, that is a mixture, and this is called mixing distribution. So I will look at the mixture, a finite mixture model from this perspective, looking at it as a Bayesian non-parametric mixture model. The goal, as I mentioned before, will be density estimation. And when I want to perform density estimation, I have to look at the posterior distribution of this new parameter P, that is the random measure that I just defined, or will be cluster analysis. And when I will want to perform cluster analysis, I have to look at the posterior distribution of the partition of the data induced by the random measure P. And I will be much more clear in what I mean, what I'm denoting with the rho, the random partition induced by P. The goal of this talk is from one side to introduce a new class of prior that encompass the standard finite Dirichlet process, and on the other hand, to introduce an easy algorithm to perform inference under a finite dimensional mixture model. But before I describe these two tasks, let me just review some work that is already out there in our community. As I told you, there are two approaches to tackle mixture model. There is some statisticians that prefer to use the parametric approach. Usually in the parametric approach, M is assumed finite, so less than infinity. Usually, as I told you, the weights of the mixture are distributed according to a Dirichlet distribution with all parameters equal. And the location of the parameter of the distribution are IID from ascending measure P-naughts. Now, how people perform inference under this model? Two options. One option is to let M fixed, no random, then fit several mixture models for different value of M, and pick the M, the number of components that satisfy some optimality condition. However, from a Bayesian point of view, I prefer the second approach, where M is assumed random, so we have to learn about the number of components from the data. However, from a computational point of view, this introduces a new layer of difficulties, because when m is random, the parameter w and the parameter tau are can change dimension. Then we have to build trans-dimensional Markov chain Monte Carlo, and usually we have to resort to reversible jumps. However, one goal of this talk is to propose some alternative to the reversible jump, borrowing strategies from the Bayesian non-parametric approach. Let me mention that this idea of borrowing strategy from Bayesian non-parametric approach and bring it to the parametric approach is not new. Already Miller and Harrison have introduced an alternative to the reversible jump by defining what we will call marginal Gibbs sampler for a finite mixture model. But so what we can borrow? What is out there for a non-parametric mixture model, for infinite mixture model? Here I have to say that the literature is really vast. There is a lot of paper dealing with the computation under infinite mixture model. There are several models and several algorithms. Here I will focus on the algorithm for the class of normalized completely random measure. Essentially, normalized completely random measure are still random measure where this sum is to plus infinity instead of m. Now, the approach to deal with computation under this prior can be split in two. There are the first class of algorithm that is called marginal Gibbs sampler algorithms. Essentially, what people do under this class of algorithm, since this parameter is infinite dimensional, it's a little bit difficult to build a Markov chain Monte Carlo on an infinite dimensional parameter. So the idea is to integrate output. This will give us a representation of the process in terms of the Chinese restaurant process. And the Chinese restaurant process allows to build a marginal Gibbs sampler that is a class of quite, let me see, relatively easy algorithm to implement that, however, give us a limited estimation. If we want a full Bayesian estimation, we have to resort to the class of conditional algorithm. Now, in this class, we use some trick to let this infinite dimensional parameter still be part of the Markov chain Monte Carlo algorithm. The main algorithm in this family is for sure the slice sampler of Cully, Griffin, and Walker. However, in this family of conditional methods, there is a subfamily that is called family of algorithms based on truncation. So what people does when performing truncation? Essentially, they truncate this infinite sum to a finite point m. So already people in this non-parametrics is using finite dimensional model to approximate infinite dimensional model. So you see that already is quite popular borrowed idea from the finite dimensional to the infinite dimensional and vice versa, but there wasn't out there a work that was rejoining these two works and look at both from the same perspective. So this was a preview of what I'm going to discuss. An outline of what I'm going to do now. I'm going to introduce a new class of mixing measure for finite mixture model, and I will call this class normalized independent finite point process. Then I will discuss the clustering induced by a normalized IFFP. I will give you the posterior characterization so that we will be able to build both a marginal Gibbs sampler and a conditional Gibbs sampler. So I will just put all the ingredients together to define a normalized IFPP mixture model, I will briefly describe the conditional algorithm based on this posterior characterization, and then I will really quickly go through this illustrative example made on the super popular Galaxy dataset. Okay, I have to build my new class of process for finite mixture model. This class of process is based on finite point process. So I need to tell you what is a finite point process. A finite point process is just a random set with a random number of elements, M, and random atoms, S1, Sn. So to define this random object, I need two ingredients. The first one is a distribution on the integer that I will denote by Qm that tells me how many points there are in this set S. Now, given that the points are M, I need a joint distribution for the vector S1, Sm that I will denote by capital H. Since a point process is a set, the order of the atoms is not important. So I need this capital HM to be symmetric. Now, the next slide is a little bit technical. From a probabilistic point of view, to study finite point process, instead of using both Qm and Hm, we prefer to work with just one function that is called Janossi measure. This Janossi measure just put together the prior or the probability of having M point, Qm, with the joint distribution of the atom. Now, it's not important that you, for this talk, it's not important that you deeply understand what is a Janossi density. However, what is important is to understand that the interpretation of a Janossi density is quite standard. Jm, ds1, dsm represent just the probability that my point process is made of exactly m points, one of each belonging to the distinct infinitesimal regions Si, Si plus S. Now, why I had to introduce the Janossi measure? Because now I'm ready to introduce my new class of prior for finite mixture model. The prior, as I told you before, is called normalized IFFP, and I will use this notation to denote this prior. And essentially, P, normalized IFPP is an almost sure discrete random probability measure whose weights are obtained by normalization of a point process S1, Sn. This point process is a finite point process such that its Janossi density has this representation here. And essentially, what is telling me this representation? It's just telling me that the capital H that I had before, that I recall you is the joint density of the atoms, can be factorized in M univariate marginal. So essentially, my independent finite point process is such that the atoms are conditionally independent. Moreover, the support of my measure is made of IID point from the centering measure P nodes, and the point process and the atom, the point process and the support point are independent of each other. So maybe instead of a mathematical definition, a cartoon will be much more easy to understand. If you want to draw a measure P that is a normalized IFPP, what we have to do? First of all, we have to choose the number of atoms. For instance, here I have m equal to 80. Then I will choose 80 points that are the support of my measure. These are these tau g. Now, to each tau g, I will attach weights. These weights are the Sj, are the atoms or my point process. Now, I need this to be a probability measure. Then I have to normalize my weights. And here I have a realization of a norm IFPP. An example, the finite Dirichlet process, that is the standard prior for finite mixture model, can be obtained by normalization. In fact, for instance, if I choose the number of components to be distributed as a shifted Poisson, then I sample m value from a gamma density with the first parameter calligraphic gamma and second parameter 1. Then if I normalize m gamma, I obtain a vector that is a Dirichlet random variable. So you see that the finite Dirichlet process, that is the process that usually is adopted for mixture model, can be obtained by normalization, as I show you in this slide. Now, before I give you some property of the norm IFPP, let me point out something that is quite important when dealing with mixture model. Several times when dealing with mixture model, we mix confusion between component and cluster. So let me be more precise. This is a mixture model with 5 components. You see, you can recognize the 5 modes. I draw 500 observations from this mixture model. And as you can see, I never obtain data coming from this subpopulation and this other subpopulation. So in some way, just 3 of the components of my mixture were allocated. So I call number of cluster the number of allocated components. So the number of clusters on my data are 3. And the number of non-allocated clusters are 2. So the number of non-allocated components are 2. So the number of components is m. When I have a sample from a mixture, I can define the number of clusters that is just the number of allocated components. Now, what I would like to show you is how the law of a normalized independent finite point process induce a prior on the number of clusters, that is, on the number of allocated components. So, how this prior can be studied? So, first of all, let me consider a sample θ1, θn from my measure P. Since P is almost surely discrete, with probability greater than 0, I will have ties among these theta. What that means? That θ1, for instance, if you look at this example, you say θ1 can be red, θ2 can be green, then I have θ3 can be red, θ4 can be blue, and so on. So I will call θ1 star, θk star the unique value among the theta. So in my example will be red, green, and blue. And then I will define a clustering by saying that an individual belongs to cluster J if and only if theta I is equal to theta j. So an individual belongs to the cluster of red just if his color is red. Now, with this construction, it's possible to show that we can write down the prior distribution that the mixing measure P induce on the clustering. This is done by the exchangeable partition probability function, also called EPPF, introduced by Pittman in 1996. And we have this formula to compute the PPF, that is the prior on the cluster induced by a norm IFFP. Now, what we have done in our work, we elaborated a little bit this formula, and we were able to show that the ePPF of a normalized IFPP assume this analytical form here, where I have an integral respect to u. I have this capital psi that is an infinite sum that depends on calligraphic psi, that is the Laplace transform of Hs. I recall you that Hs is the marginal distribution of the atom of my jumps. And I have also the product of this kappa function. These kappa functions are called cumulants and are the derivative of the Laplace transform of H. Now, why is it important to have such a formula? Why, from a statistical point of view, is important to have an expression for the ePPF? Now, the first advantage of having a closed form for the ePPF is that to have an ePPF allows us to make computation, to implement an algorithm. In particular, the ePPF allows us to provide a Chinese restaurant representation of the clustering row. And if you remember, when in Bayesian parametrics we have a Chinese restaurant representation, we are able to devise to build a conditional algorithm. Not only to have ePPF allow us to work out some theoretical property of our prior. For instance, we can write down exactly the prior distribution induced by the process on the number of allocated components. However, the formula that we have for the PPF is a little bit difficult. It involves an integral respect to u, first difficulty, then an infinite sum, and then the Laplace transform. So how we can deal with these three difficulties here? Let me go point by point. How we can get rid of the integral respect to u? Here the idea is very simple. Take the ePPF and just cancel the integral. You see here, I'm taking the formula of the ePPF, I'm just canceling the integral. And what I'm saying the function that I obtain is not the prior probability on the random partition, but is the joint distribution of the random partition and of a latent variable that I denote by u. Now, may I really do that? May I really cancel this integral? Now, I can do that if I show that the marginal law of this latent variable u does exist. And we were able to show that this marginal law exists. U is a well-defined random variable. So we are allowed to perform this disintegration operation and introduce the joint distribution of the random partition and the latent variable u. And this allows us to build a very simple generalized Chinese restaurant process that defines in a unique way the clustering induced by P. So the metaphor of the generalized Chinese restaurant process is quite standard. We think at our data as they were client of a Chinese restaurant with infinite table. The table are the cluster. The first customer enter and sit at the first available data, and we also draw the latent variable u. Then the second customer arrive and it has two options. It can sit to a new not occupied table, and this will happen with the probability that is just the ratio of this augmented ePPF. And so we have a simplified formula that you can see here. Another option is that the new client sit to the say an already occupied table. And this will happen with probability that is proportional to these two, the ratio of these two augmented EPPF. And still, we were able to simplify this formula. This is just a ratio of these two functions k. So you see, this integration trick give us the opportunity of build a very nice representation of the clustering induced by P. But we still have, clearly, since we are working in augmented space, we have also to draw the value of u of our latent variable. But now we have some other difficulty here. We have this infinite sum in capital Psi. How we deal with this infinite sum? We use a very simple concept in visual statistics, a basic concept in visual statistics. That is the concept of conjugacy. This infinite sum, if we look at it in detail, if you remember the fact that Psi of u is a Laplace transform. A Laplace transform is always smaller than 1. So this is a Bernoulli series. So we have just to choose the prior on the number of components in such a way that is conjugate to this infinite sum. Indeed, if we choose the prior on the number of components to be a shifted Poisson, we were able to solve the infinite sum, and we have this very simple and nice analytical representation of the function psi. In the same way, if m is a negative binomial, we have a nice representation of capital psi. And if for some reason we want to assume m to be fixed, so if we want a mixture model with a fixed number of components, also we have a nice representation of the function psi. So you see, by conjugacy, we are able to solve infinite sum. Concept similar to the conjugacy, the Laplace transform is available in a closed analytical form for some standard densities. For instance, if you choose the atom of our point process to be gamma, we have a finite Dirichlet process, and the Laplace transform is available in this guy here, and also its cumulant, that are the derivative of this psi, are available in a closed form. Another example, we can choose Sj to be the atom of our point process to be uniform between Z and 1, and still we have the Laplace transform its cumulant. Or we can adopt a reverse approach. What we can do? We can choose a Laplace transform, and we know that a Laplace transform identifies in a unique way the density of S via, for instance, this integral representation. Now, I want to mention this approach just because even if in the parametric framework, this is not straightforward, right? It's quite unusual. I prefer to define the density of this S. But however, in the non-parametric framework, it's much more common to use this second approach, to choose the Levy intensity, that is the Laplace transform of the function Hs, and then build the process starting from this Levy intensity. If you are interested on the theory of normalized completely random measure in infinite dimensional framework, you can look at the literature by Antonio Rio, Igor Pruster, and co-author. They have a lot of paper on this approach. Okay. For instance, here I can write down the EPPF of the finite Dirichlet process. That is always the benchmark model. And you see that it has, again, a nice analytical form. And this will simplify computation drastically. But now, let me go back one time and let me recall the concept of allocated component and non-allocated component. Remember that when I have a mixture model, the allocated component are the one that generated some data. The non-allocated component are the one that are empty. They did not generate any data. Why I'm recalling this property? because this distinction between allocated and not allocated component allow us to give the main result of this work, that is the posterior characterization of a normalized independent finite point process. So the posterior characterization is important because we are Bayesian and we look for posterior, and the P is the parameter of our model. So we are giving the posterior distribution of the parameter of interest. Now, I know that this slide is full of formulas and is difficult to read, but let's try to understand the meaning of this result. Essentially, what this result tells us? Tell us that a posteriori, if I have a sample from P, if I want to compute the posterior distribution, first of all, I have again to work in an augmented space. So I have to introduce again my latent variable u, the one that I introduced for the Chinese restaurant process. Then a posteriori, I can split my process in two parts. The part of non-allocated jump, so the part that concerns these two mode here, and the part of allocated jump. As far as the non-allocated jump is concerned, this is an independent final point process with a Janussi density that has this representation here. Now, what is important is that we were able to write down the Janussi density of this process, and this is also can assume some very easy standard form for our example. While the process of allocated jump is still a discrete measure with a fixed number of components that are the number of clusters, for instance, in this example, 3, and with weights and normalized weights that have density proportional to this formula that I have in this box. Not only, in this case, my latent variable conditional to the process of allocated and not allocated jumps is just a gamma random variable with parameter n, the sample size, and sum of all the s, the allocated and not allocated. So you see, I have all the ingredients to build my process a posteriori. But let me see how I can use this posterior characterization from a practical point of view. Let me set up a mixture. So this is a standard mixture model where it's the one that I introduced at the beginning, where the mixing measure is the finite Dirichlet process. So don't be scared by the name. It's the standard mixture model. The only degree of difficulties that I'm adding here is that I'm also letting gamma and capital lambda, that are the parameter of my process, to be random. So I'm adding an extra layer of hierarchy. Let me mention that, again, this model is well known both in non-parametric case, this is standard, but so in the parametric case, sorry, this is standard, but also in the non-parametric world, it is used as approximation of the Dirichlet process. So, may I use my posterior characterization to define an algorithm for this mixture model? The algorithm is the following one. I have to build a gift sampler on the state space that is made by my latent variable u, the parameter theta that are the cluster allocator, P, my mixing measure, capital lambda and gamma that are the parameter of P. So the posterior distribution of U given all the rest, as I told you in the theorem, is just a gamma random variable with parameter n and sum of this. The full conditional of theta given the rest is just a discrete distribution with weights that are Sj f of xi given tau j. So very easy to compute. Now what we have to do, we have to update the difficult part, the process P. But my posterior characterization tell me that I can split P in two parts, the non-allocated and the allocated jump. So for the non-allocated, what I have to do? I have to draw how many non-allocated points I have. And this is just a mixture of two Poisson random variables. So essentially here I have to draw from two Poisson. The non-allocated jump are just drawn from a gamma density with parameter updated as shown in this form. The non-allocated support are just drawn from the prior. So all standard full conditional. As far as the allocated component, okay, the number of allocated component is fixed and is k, the number of clusters. The weights of the non-allocated component are gamma with this update parameter. The location of the updated component are just obtained by a parametric update of a model where the sampling, a Bayesian model, where the sampling model is F and the prior is Pinot. So this is just a parametric Bayesian model. So you can see that all the steps of this give sampler are standard, are available in closed form. And this algorithm is a trans-dimensional algorithm. So this is an alternative to the reversible jump that doesn't need any proposal. Everything is automatic and given by the model. So I don't know if you never implemented a reversible jump. In the reversible jump, you have to tailor the proposal to jump across dimension. Here you don't have to do it because it will be just the sampling from non-allocated component that will allow you to jump across components. Finally, the full conditional of the hyperparameter gamma and lambda. Also, for lambda, this is still a mixture of gamma, while for the gamma parameter, this is the only non-standard full conditional, and we have to use a metropolis step if you want to update this parameter. So the main message is that, okay, there is a theory that I can understand is a little bit dense. There is a lot of information, but the resulting algorithm is quite easy to implement because it's made by full conditional that are all available in closed form and conjugate. Now, an illustrative example to show you how this algorithm, how to perform the standard reversible jump. What we have done, we have used a standard dataset that is the Galaxy dataset that for some reason is the dataset that people dealing with mixture use when studying new method or new algorithm. So we did the exercise of going through the Galaxy dataset by implementing a mixture model where the kernel are Gaussian. The prior, the centering measure is the conjugate normal inverse gamma. And the hyperparameter are the standard hyperparameter that I took from the literature. The results that we obtain are summarized in this slide. What I have done here, I'm just comparing the reversible jump implemented in this R package that is called MixAK with my blocked sampler. How I compare the two algorithms, I using this index that is quite similar to the effective sample size, but is a little bit more complete. The index is called integrated autocorrelation time. Essentially, smaller is this index, better is the algorithm, better are the performance of the algorithm. And you can see how our algorithm is going much better than the reversible jump, in particular way when lambda is large. Now, lambda large means a mixture with a lot of components. So when I'm dealing with mixture with several components, my algorithm drastically overperforms the reversible jump. Just another thing. is well known in the theory of finite mixture model that is convenient to set mixture with a large number of components. These mixtures are called sparse mixture model. Why? Because there is some theoretical result by Rousseau and Mengersen that show how mixture model in this case is consistent. So a posteriori, the posterior distribution will converge to the true distribution that generated it. What I have done here, how we obtain sparsity in our under our approach. We obtain sparsity by letting lambda large and gamma small. But I'm going to see, if I let these two parameters random, the data will push my model to be sparse. So the answer is yes. Why the answer is yes? Because these two parameters a posteriori is a high correlated. And you can see that when lambda becomes small, when gamma becomes small, lambda becomes large. This showing that in some way the model is looking for sparsity. But the advantage of having these two parameters random is that the random parameter allow also for a parsimonious model. In fact, you can see that a posteriori the number of non-allocated jump is not so large as in the case when I have 1000 component, but is small with other detail, but still small. Okay, I think that these are all the information that I want to share with you. Just to wrap up what I have done, I have studied the finite mixture model, but from a different perspective, from a Bayesian non-parametric perspective. This allowed me to introduce a new class of prior for finite mixture model that I call normalized independent finite point process. We studied the theoretical property of this prior. In particular, we gave analytical closed expression for the EPPF, the exchangeable partition probability function, and we also gave a characterization of the posterior law of this random measure. We designed a conjugate block key sampler for finite mixture model, and we show how this key sampler outperform the reversible jump in terms of integrated autocorrelation time. And in the last slide, I also show you how the model will induce automatically sparsity in the mixture model. And this is all. Thank you for your attention. If you are interested, a preliminary version of the paper is available on archive at this address. Thank you very much.
Oi, Raffaele. Thank you so much. Very nice, the paper. Very nice. There is some questions for Raffaele. We should wait a little bit, Raffaele. I have some questions for you. Very nice. I have, when you introduce the model, how do you compare it with the Dirichlet process? In the following way, because when you define the process there at the beginning, what you did that is different, if I understand well, is to define the weights in the measure, because we define the weights in a different way than the Dirichlet process no?
Yeah. But I think that to understand the link with the Dirichlet process, you can look at this slide here. Maybe I was running a bit. What is well known that if you have a Dirichlet distribution, let's say a Dirichlet distribution, okay, for the W, And if you put your Dirichlet distribution, the parameter equal to a number k over lambda, and then you let this lambda goes to plus infinity. So when this lambda is large, you obtain as limit the Dirichlet process. So, so it's just a property. So this means that if you have a mixture with a lot of with m large, and you put gamma equal to half kappa over m, you are very near to the Dirichlet process.
Okay. Then, yes, one thing that I have noticed in the Dirichlet process is that in general, when you are using it for clustering, usually you have more components, more clusters than you really need to describe the behavior of the data. That means the Dirichlet process identify more clusters than it should.
Yeah. Okay.
How this normalized finite point process works in this direction? How do you compare it?
Okay, so let me mention. Our model is consistent. This means that when we have infinite data, we can estimate properly the number of clusters. Okay, and the number of components coincide. We can show that is consistent. Now, in the real case, when n is finite, I think that still, and this is true for all mixture models, you have to take care of how you fix this parameter. Okay, this gamma and lambda. So the best way is, as I have done here, to fit some prior. However, I think that is slightly better, is a little bit better, but still you can obtain this get richer behavior that you were mentioning about the Dirichlet process. I don't think that this will outperform the Dirichlet process drastically, let me say. It's a little bit better, but I don't think that will be a huge difference.
Have you tried different priors for lambda and?
Yeah. We try. Different prior. We use actually. Here I didn't have time. In this case, the number of components are always assumed to be shifted Poisson, but we also use negative binomial. And we also use different process, different from the final Dirichlet process. We use the sigma stable process. Actually, for instance, there are some process. There is one process that is called sigma stable finite point process. And I think that the sigma stable finite point process is working much better in terms of clustering. But from a computational point of view, it's a little bit more expensive. Or computation is a little bit heavier.
Let me check if someone has some question for you. I have a comment here for a while that is from Frederico. I don't know if you can read it.
Yeah, I think that I can read. Thank you, Federico.
Let me check if someone have questions before. Not yet. Well, then I will continue with my questions for you.
Thank you. We have a lot of questions.
Yeah, I have. I have because, in fact, it was so interesting, this process, in fact. But many of this process usually works with exchangeable clustering processes, no? And have you tried to use it in the context of non-exchangeable partition?
Okay,
how does it work in this case?
This is a very interesting question, actually, and this is the next step. Let me see.
Good.
So what we are doing, we are using, we are using the process for the repulsive mixture model. So repulsive means that the atoms, the mu, the theta here, are repulsive. Okay, so they are not IID, but they are dependent because they are repulsive each other. And it is working quite well for this cluster model. Now, the next step will be to use that for spatial clustering or for time series clustering. So we would like to induce spatial dependence and time dependence. But we are still at the beginning of this project. So I think that since I'm slow in my research, I will need a little bit of time to have some results. But yes, I think this is really the direction where this process can give some very nice results.
Yeah, because you are using the Pitman representation, no?
Yeah,
I guess.
Yeah.
I guess.
But I think that you can work out in some way, some alternative way, and still use the Pitman representation also in the non-exchangeable partition, let me say.
Yeah. I guess Fabian, I don't remember his surname. Fabian and Ramsés, I guess they have some exchangeable clustering models. Yeah, very good. Raffaele, no one has questions for you.
Okay, thank you to everyone. Muito obrigado.
But I still have one that is infinite that far?
Not yet. What I'm saying, the main message is that no. Actually, what I think after this work is that sometimes, I don't know why, there is this tendency to say, oh, I would like to use finite, I would like to use infinite, but with this work we show that both finite and infinite mixture model can be tackled, can be studied using exactly the same object, exactly the same algorithm, and they produce results that are similar to each other. So I think that infinite is very near.
Very near.
It's just the important is to look at it as it is here.
There's a question for you.
There is something about finite Dirichlet process with space-time cluster. Not yet. I'm working on it. Patricia, thank you for your question. As Rosangela mentioned, there are a lot of work on Dirichlet process for space-time cluster. There are a lot of work by Ramses Mena, Peter Mueller, Fernando Quintana, Page, trying to use infinite dimensional mixture for space-time cluster. There is also work by my colleague Lucia Pasci that actually use a finite Dirichlet process, I have to say. So there is something around. If you send me an email, I can provide you with a little bit of literature, but mainly in the infinite dimensional framework. About the finite dimensional framework, there is a little bit.
Okay. Well, if no one has more questions, I just like to thank you, Raffaele.
Thank you to everyone. Obrigado again. Obrigado. I hope that you enjoyed the talk.
Yeah. Bom fim de semana para todo mundo. Muito obrigado por participarem. Na próxima semana nós teremos outro convidado internacional, que vai ser Ramsés Mena, lá do México. Então vamos continuar com a não paramétrica. Tá certo? Raffaele, eu não tenho como, de fato, agradecer você por você ter aceitado o convite e feito tão em cima da hora. Tá certo?
Ha sido um prazer.
Isso. Quase um português.
Quase português.
Muito obrigada para todo mundo.
Muito obrigado. Boa tarde.